turbo engine running.
Absolute genius.
Get this.
Welcome.
This is the show where we bring you
Science.
What that essentially means is
discoveries,
Advances.
Questions. Research.
technology.
Unbelievable.
Without further ado,
This is The Naked Scientists. Hello, welcome to The Naked Scientists podcast, the programme that brings you the biggest breakthroughs and talks to the major movers and shakers in the worlds of science, technology and medicine. I'm Chris Smith, and coming up, scientists solve the mystery of how the Mantis shrimp can KO its prey with a knockout punch but not injure itself in the process. Also, researchers discover why rice makes methane and engineer a new methane-free form into the bargain to feed the planet. And we find out about Donald Trump's new NASA director. Just who is Jared Isaacman?
From Cambridge University's Institute of Continuing Education, this is The Naked Scientists.
Up first this week, the Mantis shrimp is well known for packing a gigantic punch. It's so powerful, in fact, they're able to smash the shell of a prey animal with a force equivalent to a sledgehammer swung at full pelt. But if it's socking its opponent sufficiently hard to knock it into next week, why doesn't the shrimp knock itself out in the process? Somehow, it seems to be able to shield itself from that incredible force, and now scientists in the United States have sussed it out. It's all down to the cleverly evolved structure of the shrimp's club, which can dampen shockwaves so they don't propagate back into the animal's own body. Graham McShane is a fellow at Queen's College in Cambridge, where he works on artificial structures just like these, and I asked him for his thoughts on the new study.
So what they've been looking at is this mantis shrimp, which has this adapted leg, this dactyl club that it uses to attack its prey. And it's got remarkable features because it strikes the prey with this club with such force. The force is 1,000 times the weight of this little shrimp. And the question is, well, how does this shrimp attack its prey in this way without injuring itself? And it can attack its prey hundreds and hundreds of times with this club, but not injure itself. And so what the researchers were trying to understand is, what are the mechanisms at play here that allows this material to behave in such a way? Because, if we can understand the mechanisms, we can design materials with these properties for our own use.
I suppose in some respects, Newton's third law says if I hit you really hard, I feel the same pain that you do because the same force is coming back into me. So it's how does the shrimp exert that huge force and the force coming back not then knock out the shrimp?
Absolutely. So the shrimp has got this very clever design of its club where it can almost spring load its club to launch it at its prey, and it strikes the prey with tremendous force. And as you say, that then sends a huge shockwave back through the club and into the shrimp. And the question is, how does the shrimp dissipate that, or how does the design of the club dissipate that? And I think researchers have been aware of a couple of different mechanisms for a while. And so they've understood that the architecture of this club is such that it avoids the club shattering. It's an incredibly hard, incredibly tough material. And they've looked at the structure of it, and they've realised it's got this hierarchical structure. It's made up of these fibres of biopolymer, which are then grouped together in bundles. And then these bundles are themselves grouped together in layers. And then these layers are then stacked on top of each other in different arrangements. And they've understood that that's what gives this club its incredible toughness, because cracks don't propagate very easily through that material. So that avoids the club shattering. But in this latest study, they're also thinking about the shockwave that travels through that club. So how does that shockwave then not injure the shrimp? And what they've realised is that the architecture of this material of this club is able to dissipate the energy of that shock in a very effective way. It's called an acoustic metamaterial. It can manipulate the way waves propagate through it using this architecture of the material. And they've developed some very clever experiments to really try to study this effect and to understand what's going on as these shockwaves propagate through the material and then how they're dissipated at this microstructural level.
I was just going to ask that, which is, this is small, the vibrations are incredibly fast. Yeah. So how are they actually watching what happens inside this creature's club as it uses it?
Absolutely. So they're using very clever techniques with lasers. So they're using lasers which they're reflecting off the surface of the material, and they can use that to excite the material. So the lasers can locally heat the material, which can cause elastic waves to propagate through the material. And then they can use a similar technique to look at how the material is responding. So they're able to take very fine measurements at very small scales to measure essentially the sound waves as they're propagating through the material and study how they're reflected and how they're dissipated within the material. And that gives them the data that they need to understand these mechanisms.
Is it effectively then a baseball bat but with a really good shock absorbing handle, so I can hit someone really hard with it, not that I would, and what comes back up my arm is a fraction of the force that hit the person very hard and knocked them out?
Absolutely right. And so what's going on is, if you imagine the handle of that baseball bat has got a very clever microstructure like the one I described, such that when the shockwave tries to propagate through the handle, it reflects internally in complicated ways around this microstructure. And those internal reflections can cancel each other out and they can dissipate. And so the shockwave is blunted and that energy is absorbed so that you never feel it in your hand. And so it's a very clever way of dissipating that shock so it doesn't injure the mantis or you holding your baseball bat.
Can we use this? Because it sounds to me like there are a lot of different possible applications. Now we understand how this is working. Can we steal it, basically?
Absolutely. So there's a huge number of applications where we can use this kind of thing. We can think about protective equipment, so helmets, body armor, where sometimes it's not enough to just stop something that's hitting you. You also need to deal with the shockwave that propagates through as a result as well and dissipate that. So we could come up with clever ways of designing liners for helmets, as well as very tough and hard surfaces that will stop projectiles and so on. We could think about protection of buildings, so protecting buildings against shocks and earthquakes, so absorbing the energy of those shock waves without causing fragmentation and damage of the buildings. And crash protection for vehicles, shock protection for sensitive things like sensitive equipment, batteries, electronics, and so on. So we can look at nature and we can learn from the mechanisms that are at play, and also the way nature combines lots of different functions together in a single material. We can learn from that to create effective and efficient materials. The challenge for us is understanding those mechanisms and then understanding how we can fabricate materials that deliver those mechanisms on an engineering basis.
Nature never ceases to amaze me. That was Graham McShane from Cambridge University taking a look at that study, which has just been published in Science. Now here's a powerful statistic for you. Over half the planet's population depend on rice for the majority of their calories. But current rice cultivation, in turn, is responsible for 12% of global methane emissions. And these emissions are expected to increase with global warming and also through a rise in human population. So it's a big player. Well, now scientists have identified the chemical compounds that are released by rice roots that drive that production of methane. This information has then enabled them to breed a new, high-yielding strain of rice by crossing the non-methane-emitting variety they had with an existing crop rice to produce a form of the plant that doesn't release these chemicals and consequently emits up to 70% less methane. I've been speaking to Anna Schnurre, who's a biologist at the Swedish University of Agricultural Sciences, where she did the work.
Rice cultivation leads to a lot of methane, and methane is a very strong climate gas. So by growing a lot of rice, because we also need food for the growing human population, we actually create a problem with a lot of methane going out to the atmosphere.
Is the methane produced by the rice plant, or is it produced by the conditions the rice is growing in?
So it's not produced by the rice plant itself, but the rice plant helps because the rice plant release different type of chemicals around the roots, and these compounds can be used by different microorganisms in the soil, and as a result we get methane that is produced.
So the rice is making the problem happen, but it's because it's feeding the wrong sort of microbes, effectively?
Yes, exactly. So our approach have been to try to understand more exactly what is released from the roots of the rice plants and in what way these compounds feed the microbes. So there is a collaboration between the rice plant and the roots and the microbes. They are helping each other, so to say. So it's a good thing that you have microorganisms in the soil around the roots. But we don't want the wrong microorganisms to grow.
How did you track that then to work out what it was that the rice was releasing that feeds the microbes that then turns into methane?
We had two different type of rice plants, one that had a low emission of methane and one that had quite high emissions. And then we compared these two plants. So we did a chemical analysis of the compounds that were released from the plants to try to see, is there a difference between them? And if there is a difference, what is the actual compound that differ between these two rice? And doing so, we could actually detect the compound that was specifically linked to the methane production.
Ah, right. And so the form of rice that doesn't produce as much methane produces less of these compounds from its roots.
Yes, so there is an organic compound called fumarate, and this organic compound is used by the microbes as food, and then it's converted into methane, which is then released from the rice fields.
And does the rice have to get rid of that fumarate in order to be healthy? So when you compare these two rice plants, the one that does and the one that doesn't make methane, is the one that doesn't produce methane from its roots less healthy, or is it perfectly happy and the yield is the same?
Yeah, yeah, it's actually perfectly happy because it's not only this fumarate that is released, it's a lot of different type of compounds. And all these different compounds are food for the microbes in the soil. But fumarate is very specifically linked to the microbes that are releasing the methane.
Given that you've got a form of rice then that doesn't produce much methane, have you solved the problem? Do we just grow that everywhere? Or is that just a laboratory specimen that's good in some respects for studying, but it's not a high-yielding variety we could feed the world with?
Yeah, this rice is actually a high-yielding variety. So what we have done is that we found this low methane emitting rice, and then we have crossbred it with a high-yielding variety to have a rice that has both low methane and high yield. So this new variety that we have produced can actually give us both more food and at the same time reduce the amount of methane.
Brilliant. Is this now it then? It's a slam dunk. We're in a position where you can take this rice that you've bred and it should be capable of growing in all the different rice growing environments around the world, or is it fussy? Will it need further adaptation?
You can grow it in many different areas, but it can't tolerate all different types of temperature areas. So we still need to continue to breed for more similar rice varieties that can grow under different temperature conditions. So this rice can be used in many areas, but not all. So not the tropical regions, for example.
Is the next step then to take some of those tropical cultivars and cross them with your low methane variety, going for one that has the ability to tolerate the tropics, but still doesn't churn out loads of methane?
Yes, exactly.
And is that hard to do?
No, not now, I would say, because we know the mechanism, we know what we are searching for. So I think this is not a complicated thing now to do.
And so if you were able to get this across the world, something like a half the world's population depends on rice, doesn't it? The impact would be huge.
Yes. I mean, rice cultivation today represent a lot of the methane that is released into the atmosphere. And it's also increasing because the temperature is increasing. So it's like a bad loop that's going on right now. We need more food, more rice, and the temperature is already going up. And that's also increasing the activity of these methane-producing organisms in the soil. So this is a problem that we really need to take care of.
Absolutely fabulous piece of work. That was Anna Schnurrer there at the Swedish University of Agricultural Sciences, and she just published that work in the journal Molecular Plant.
The Naked Scientists podcast is produced in association with Spitfire, cost-effective voice, internet and IP engineering services for UK businesses. Find out how Spitfire can empower your company at spitfire.co.uk.
Music in the programme is sponsored by Epidemic Sound, perfect music for audio and video productions.
This is the Naked Scientists podcast with me, Chris Smith. Still to come, NASA has a new director, Jared Isaacman. So what do we know about what he might have in store for the world's foremost space institution? But first, what does a virus sound like? Now, I'm not talking about hacking and coughing and sneezing. And it may indeed seem like a strange question, but it is one that scientists have been attempting to grapple with in a bid to find out whether we can better defend ourselves against these entities and also gain new insights into how they operate inside our cells. Elad Harel at Michigan State University has got a way to shake virus particles with lasers and then listen to the vibrations to work out what shapes they are and what they're made of and how they work. It's amazing.
We wanted to know if we could track a virus by its sound. Do viruses make a sound? Can you induce them to make a sound? If they do, can we use that to track them and avoid some of the challenges with studying them nowadays?
They're also, some of them, 1/30,000th of a millimetre across. Absolutely tiny. How
Right.
on earth can you listen to something that small?
We've looked at, very small objects before. We've looked at kind of nanoscale, billionth of a meter, and we knew that we could measure these kind of vibrations. We call them acoustic vibrations. We could do it on these metal nanoparticles, but from a very naive point of view, a virus is a small nanoparticle. It's very well organized and well structured, and we thought, maybe it also produces some kind of ordered vibrations, and we wanted to know if we could pick that up. We knew approximately where we would be looking. It's about a frequency that's 1 million times higher than what humans can hear. It's something that you need, very specialized instrumentation to detect. And the challenge really was the fact that a virus is, embedded in a very complex environment. If you think about a virus in a cell, there's lots of other material around it, and all of these materials also give rise to different sounds. So what could we pick up the sound in the background of everything else? So this was kind of, trying to pick up the sound of, say, an insect in a forest from hundreds of meters away. That was kind of the technical challenge that we were facing.
How did you do it then? What was the apparatus that enabled you to tune in to the sound of a virus?
What was really amazing was that we could use light both to generate the sound and to detect the sound. So you can think of light as a hammer, like when you bang on the table with a hammer, you bang on a nail, you bang on the wall, you're really causing vibrations in that material. All those atoms that are in that material, in that table, in that wall, in that piece of glass, whatever it may be, they're all vibrating. So what we did is we used light as the hammer itself. So the light actually caused this virus particle to vibrate at this very, very high frequency. And then to detect that, we used another laser pulse, which actually scattered off the vibrating virus particle. We capture this in a kind of stroboscopic way. So that means that if you've ever been to a disco or to a club and you see that strobe light, all right, and it kind of flashes on and off, and you see these kind of snapshots of people moving, that's kind of the same idea where we hit this thing with a hammer, it starts vibrating, and then we wait a little bit of time, we take a picture of it, and then we repeat that over and over again, about 100 million times a second. And we build up a kind of a movie that kind of shows a sound wave that goes up and down, up and down. So this virus is really acting kind of like a very small instrument.
Just out of interest, what virus was it that you were using as your test virus here?
It was a rhinovirus, and
So the common cold, the thing that every one of us is suffering
exactly.
with at the
It was a
moment.
pseudovirus, that's right.
Did you get it from someone in the lab?
We got it from a collaborator who works.
What, from his
and
own
these are all-
nose, or did what I meant was, did someone donate the specimen of their own
No,
mucus?
not.
Because it's so common, isn't it? But more seriously, what is the purpose of this? Is it just that you're stressing the system to prove that you can do this with these tiny entities, or is it that there may well be an application to being able to probe tissue that's got things like viruses lurking in it like this?
We see its two main applications. On one hand, diagnostics. You can imagine, now you need PCR. You can't detect whether the virus is actually, whether the infection is active or not, because the virus may have already ruptured and you're detecting really the genetic material inside of the virus. So here we have a method that we can detect the virus at the single virus level. That's just one virus particle. So we have kind of the ultimate limit of sensitivity. And so you could imagine detecting viruses very, very early on before the onset of any symptoms. And because you can do it with light, you could even do it at a distance without making any physical contact. On the other hand, we're primarily interested in the applications, understanding how viruses actually function. What are the dynamics of viruses? How does a virus assemble? How does a virus disassemble? How does a virus attach to a receptor? How does it get brought into the cell? If you can track that in real time, which is what we're trying to do now, you could develop antivirals by targeting any part of the virus life cycle to really speed up and streamline that process of trying to understand how drugs interrupt the binding or some other process where viruses can replicate and can infect you and make you sick.
Cool, isn't it? That was Elad Harel at Michigan State University. He just published that discovery in PNAS. The US space agency NASA has been in a state of flux for a number of years, and it now has to compete with a number of private companies who are seeking to challenge its dominance. It also now has a new boss because, traditionally, the director is replaced by an incoming president. And Donald Trump's pick for NASA chief, Jared Isaacman, has raised a few eyebrows. Isaacman doesn't have any NASA experience, but what he does have is lots of money, and he's worked with some of the major players in the US space industry. And he's also been into space. I asked Richard Hollingham from the Space Boffins podcast to tell us a bit more about him.
Oh, he's fascinating. Well, he's another tech billionaire, and he was born in 1983. He created his first tech company at 15. It's a payment processing company. He then branched out into a defense company that trains US Air Force pilots. He's got a passion for flying. He's got a passion for space flight. He led the first private space mission. He took part in the first private spacewalk. In fact, as an astronaut, he has gone higher, or that crew went higher than any astronaut since the Apollo missions of 1972. So as an astronaut and as an astronaut pioneer, he has certainly got the right stuff, if you like, for doing that.
He does sound uniquely well qualified, actually, for this job.
Well, he's probably uniquely well qualified to, push forward astronauts, human spaceflight, missions to the moon, missions to Mars. But NASA is so much more than that because, of course, it does exploration missions like the amazing James Webb Space Telescope that's giving us these just stunning images of the most distant galaxies and also our own planets. It also has a lot of Earth observation missions, so giving us that sort of eye on the planet and what's going on. So NASA is lots more than that. It also has a whole flight division where they're looking into innovations in flight. So, for example, NASA developed fly-by-wire technology, which is in every aircraft. So NASA is a lot bigger than just sending astronauts to the moon and Mars.
But he is a pilot, isn't he? I mean, Isaac.
Yeah, he is, absolutely.
He flies stunts at air shows and things. He flies jets.
And it's not a surprise that he's been nominated to become the new head of NASA by Donald Trump, given that Donald Trump mentioned in his inauguration speech, I was listening to the speech, said, what? He just mentioned Mars, I had to spool back and hear that again. So, Donald Trump said, we will put an American on Mars. That is not the current NASA plan. The current NASA plan is to return humans to the moon and have the first woman on the moon. So, I mean, straight away there, you've got something very different in the offing.
He also said, that's Donald Trump, he said, Jared will drive NASA's mission of discovery and inspiration, paving the way for groundbreaking achievements in space science, technology and exploration. I mean, that does sound on message. So what are the people who are objecting to this saying then? What's the controversy?
Yeah, well, very few people have actually said he's the wrong person, because you could argue that the former head of NASA, Bill Nelson, and almost the equivalent of a private astronaut. So Bill Nelson had flown in the space shuttle, but as a congressman, as a politician on the space shuttle. And when you talk, I can't really share with you what some of his crew members said about him at the time, but they very much, the shuttle crews very much considered these politicians in space as self-loading cargo, if you like, on these missions. So, it's always a political appointment, the head of NASA.
So do you think then that because he's run very successful companies and is a tech billionaire, but doesn't necessarily have yet the political experience, that might be something that people are saying is a weakness because he's got to go and deal with politicians.
Yeah, so you've got the billionaires, or the millionaires, if you like. You've got Donald Trump talking about going to Mars. You've got Elon Musk developing these incredible, whatever you think about Elon Musk, he's developed these incredible spacecraft and Starship, which is the one that's currently in development, that he wants to take people to Mars. You've got Isaacman. You've also got, don't forget, Jeff Bezos, who is developed the New Glenn rocket as well, which is, that's going to give Musk and SpaceX a run for their money. And then you've got, in the other corner, the NASA way of doing things, which takes a lot longer, but also involves a lot of people, and a lot of people who are often in Republican areas. So, particularly with the current plan to send people to the moon is to use a brand new rocket called the SLS, Space Launch System. A giant rocket, looks very much like a sort of mash-up between the Apollo Saturn V rocket and the Space Shuttle. So it's a big rocket, big tube with two solid boosters on the side. That has been developed in Huntsville, Alabama, Republican territory. So you've got that. So if you start taking that away, if you start saying, well, the SLS isn't really going to do it, let's use Starship instead, which would make a lot of sense, there is going to be a political backlash to that. So it's got to be handled carefully. But the SLS, it just looks so old-fashioned compared to what Elon Musk is developing and what Jeff Bezos is developing, that inevitably, even if they fly the ones they've built, they probably won't build any more. So that's the old way of doing it, and now you've got the new way of doing it, which, Jared Isaacman very much represents that.
Richard Hollingham from the Space Boffins podcast, and their latest episode is just out on our Naked Astronomy feed, actually. So head on over to nakedscientist.com/astronomy if you want to hear a bit more about what's going on above our heads without going over our heads. That's from Richard. Well, now it's time for Question of the Week, and James Titko is looking into this sound-based query from one of our loyal listeners.
My name is Bill, and I'm sending this message all the way from Ballarat in Australia. I listen to bone conduction earphones in preference to conventional headphones or earbuds. As I'm a keen fisherman and bike rider, I like to hear environmental noise around me like cars or fish splashing. At times, due to louder environmental noise, like the motor of my boat whilst cruising, I need to raise the volume and receive warnings via my smartphone. Neither environmental noise or speaker volume seem excessive or cause discomfort. My question is, do bone induction headphones without earplugs pose the same risk to hearing loss as conventional headphones or speakers? Thank you.
Thank you, Bill. When paying attention to sound in the environment, or when listening to the Naked Scientist podcast through traditional headphones, sound waves are being funneled through your outer ear to the eardrum, causing it to vibrate. The vibrations are focused by 3 tiny bones in the middle ear and eventually reach the cochlea, a spiral-shaped organ in which the movement of fluid stimulates tiny hair cells, converting mechanical vibrations into electrical signals which our brain can interpret. But what about bone conduction headphones? How do they work, and do they pose a risk to our hearing in the same way as headphones that sit in or on our ears might? I've been speaking with Roger Lewin, audiologist at the Knutsford Hearing Centre.
Thanks, James. Bone conduction headphones work by converting sound into vibrations that are transmitted through your skull directly to your cochlea. This process bypasses the outer and middle ear and has enabled people who have problems in those areas, those with issues like ear infections, malformations or fluid build-up, for example, to hear better.
Beethoven famously used a primitive form of bone conduction as his hearing deteriorated, biting down on a rod placed against his piano, giving the vibrations produced by the sound of the instrument a route into his ear, through his teeth and into his skull. But what about the risks posed to our hearing from bone conduction headphones?
Noise-induced hearing loss occurs when sustained or intense sounds damage the delicate hair cells within the cochlea. The powerful vibrations created by loud sounds may overstimulate hair cells, bending them too far or too frequently. If hair cells become damaged due to repeated or intense exposure, they will not regenerate like other cells in the body, and this can lead to permanent hearing loss. Whilst bone conduction headphones are enabling sound to bypass your outer and middle ear, they're still relying on the cochlea to translate the sound vibrations into electrical impulses, and so you should still take care. Most commercially available headphones are designed with ear safety in mind, so you should adhere to the warnings from your smartphone if they're detecting high exposure. Your insight about the risk increasing when turning the headphones up to overcome engine noise is correct. This often happens with normal air conduction headphones too. If you're able to enjoy somebody else's music secondhand whilst you're sitting next to them on a train, it's a sign that they are at risk of excessive noise exposure. In that circumstance, the best solution is to use headphones that reduce environmental noise rather than turning volume up.
So, Bill, make sure you're taking good care of your ears by limiting your exposure to loud noises for long durations, as bone conduction headphones do have the potential to cause damage to the cochlea in your inner ear. Thanks to audiologist Roger Lewin for helping us with that one. Next time, we'll be answering this question from Wayne.
Hey guys, thanks for answering my question. I was wondering, if fire needs oxygen to burn and there's no oxygen in space, how does the sun stay burning? Thanks.
And if you think you know the answer, remember you can have your say on this or all of our questions, in fact, over on our forum. That's at nakedscientist.com/forum. And do, of course, be sure to drop us a line by email if you think you know the answer or you have a scientific quandary of your own that you'd like us to take a look at. It's chris@thenakedscientist.com. A brief note to say thank you very much indeed to those of you who are supporting the programme with your generous donations. It makes a huge difference. We are really, really grateful. It really does help to keep the show on the road, and I'm writing to you to say so. Thank you very much indeed. And those of you who do support us on a monthly basis, you're not forgotten. I see all of those come through, and again, I'm very, very grateful. Thank you for sticking with our programme. And if you haven't yet joined the ranks of those who do show their support and you'd like to help us out with a donation here at The Naked Scientist, please go to nakedscientist.com/donate. We've made it very easy. nakedscientist.com/donate. Thank you. That's all we have time for this episode, but do join us on Tuesday when we're going to be examining how Russia uses science to undermine the West. The Naked Scientist comes to you from the University of Cambridge's Institute of Continuing Education. It is supported by Rolls-Royce. I'm Chris Smith. Thanks for listening, and until next time, goodbye.